Okay, well, we have these two examples now. Let's go on to our third example, which is polynomials. Well, I can have, now what, I always get this wrong, which is, so in here in the text, I go through and just go through these realizations of vectors. Here's the the one-dimensional arrows, and then goes on to the two-dimensional arrows. And here's the how you make the vector components with these differences and the addition. And there's some other techniques for doing that. And we'll come back to that. Okay. There's all the geometry there, and we will come back to some of those problems, but I wanted to go on and look at the parallel possibilities. Okay. So let's look at what's called P2. This is the vector space of polynomials, of quadratic polynomials. So this P2 is going to be let me make sure I use the same notation, A1 plus A2 plus A2x plus A3x squared. So this is the space of quadratic polynomials. Now, the problem here is we're never going to put a number in for x. X is a placeholder. X, a placeholder. So we're looking at these as functions, as polynomials. So the things that vary are variable. So this switches what we think of as constants and variables. X is like an indeterminate. It's a placeholder. And A1, A2, and A3, those are our variables. We have to use like these numbers, so we could say V1 equals A plus BX plus CX squared. So our variables here are A, B, and C. X is just going to be fixed. So this is one polynomial. Well, here's another one. Let's say we have 2 plus 3x plus 4x squared. Here's a third polynomial, 5 plus 2x plus x squared. So each of these is a different polynomial. We're thinking of them as functions. So, for example, so it's important here. It was clear when these were the same vector, same length, same direction. It was clear when these were the same vector, same numbers in the vectors. But what does it mean for these two to be the same? Well, it doesn't mean they're the same polynomial if they're the same for all values of x that you might put in. So we're thinking of it. So what has to happen is if I say that V3 equals V1, well, that's good. This equation here says these are the same polynomial. Well, if I wrote that out, that would be 5 plus 2x plus x squared equals A plus BX plus CX squared. Well, we don't put a value of x in and say they're equal. These are going to be the same polynomial. Is 5 equals A, 2 equals B, and 1 equals C, right? They're going to be the same polynomial if all the coefficients are the same. Polynomial. This is similar to the proof that you guys had to do in the second assignment with linear equations, when the question was, are these the same equation? Well, they're the same equation if the coefficients are the same, right? So that problem has to do with the space with P1, which is the space of this is a polynomial of linear polynomials, right? And so these are the same if the coefficients are the same. Yeah. Well, there we had two variables, x and y, so that was a little bit different. But it's similar in respect to K. Well, how do we add polynomials? So let's do this with P1. If we have 2 plus 3x, if that's V1 and V2 equals 3 plus 4x, then V1 plus V2 equals 2 plus 3 is 5, 3 plus 4 is 7x. So you just add corresponding components. The constant term gets added, the linear term gets added, the quadratic term will get added. So there's nothing mysterious going on, right? And then 3v1 would equal 3 times 2 plus 3x equals 6 plus 9x. Well, it turns out that these objects treated this way have all the same properties as these ones, as the arrows, and would have, well, except that they don't have a geometry, but in a way that these ones do, but they have all the same properties of these column vectors. Okay, so that's our third example. And let's see our fourth example. Well, let's treat, we're going to give a name to this. M34 is a special case. It's going to be the set of all A, B, no, let's do 3 times 2. Let's do 2 times 3. Since I've started there. 2 times 3 is going to be 2 rows, 3 columns. It's going to be the space of all 2 by 3 matrices, where A, B, C, D, E, F are real numbers. And the addition is just the normal of 4, 4, 4, 10, 10. It's just the normal vector matrix addition. So if I treat matrices of a given size and add them like this, I get a matrix of the same size, and instead of all these matrices, this is going to be so I'm going to think of each matrix of this size as a vector, and I can add the vectors by this means. So if this is V1 and this is V2, this will be V3, and then I can also multiply a vector here by a number to get 3, 6, 9, 12, 15, 18, just the same way. So it turns out that these two, addition and multiplication, give you the, they make this into a vector space, which we can think of it. So these are sort of our 4 standard examples, which are a little bit different. You know, this is usually we don't think of the matrices as vectors, because if you think of a vector as a column vector, well, this isn't a vector, it's because it's a matrix, right? But if we're thinking of the vectors as members of a vector space that have certain properties, then that's what we mean by vector. So what we're going to mean by vector is an object that has certain properties. And then we want to look and see what are those common properties.